So good afternoon, everyone. Thanks for joining on this Thursday afternoon. My name is Cole Fitzpatrick from UMass Amherst. We're joined today by Professor Fei Miao from the University of Connecticut, and I'll toss it over to her momentarily. Before we do, I just wanted to highlight again for our consortium members that we have a symposium coming up here just in about a month's time. This will be hosted in Worcester in conjunction with our innovation conference. So if you haven't done so yet, or you want to get some more information, I'd encourage you to go onto our website. So that's umass.edu/NEUTC. And you can learn about the event. You can register using this link here, and you can access our full agenda, which contains location information, information on the agenda, the calendar of events, as well as some parking and hotel information. So if you have questions, feel free to reach out. Otherwise, we encourage you to register. Right. With that, I will pass it over to Professor Miao for a presentation on AI.
Okay, so now I will share my screen. Hey.
Looks good.
Okay, great. Good afternoon, everyone. Happy to present my research on learning and control for safety, efficiency, and the resiliency of embodied AI. So I'm currently an associate professor at the School of Computing of UConn. So this is my 7th year at UConn, and I've been working on this for several years. So with the growing opportunities of AI and embodied AI, nowadays we see deep learning is everywhere with a large amount of data. For example, we can have better predictions. And with reinforcement learning, we see a lot of robots research going on. And hopefully in the future, we do have better systems in our daily life by deep learning. So specifically in our group, we focus on multi-agent learning or multi-robot system. The motivation is we do see that in the future, there will be a lot of scenarios like mobile warehouse, manufacturing places, transportation. We will have more than one robots in our environment, right? And then robot needs to coordinate with each other to make sure finish the task efficient and safely, etc. So, however, we are still very far away from that point. So thinking about a robot, so if we train it in simulator, we fail, that's okay, we just restart. Or if we play a game, that's okay, so no rush at all. But if it's a real system, a robot, or a real autonomous vehicle, if there is some accident, then it will be very dangerous to human life. So safety part, still we need a lot of effort to really reach that point. And efficiency is another challenge that we will have many autonomous vehicles on streets in the future, and we want to make sure these vehicles coordinate with each other very well. All the traffic flow will be, again, not efficient at all. So to reach that future goal, today we will mainly focus on our group's research on learning and control with communication capability for multi-agent systems, and we will mainly focus on this connected autonomous vehicle scenario. And if there's time, I will very briefly introduce our work on data-driven robust optimization and cyber-physical system security. So the kind of scenario we have been considering is in this connected autonomous vehicle scenario where vehicle can have communication to other vehicles on streets. It can also have communication to road infrastructure, for example. And basically, we will have a data-rich environment that there will be a lot of sensors and actuators on the streets in the same environment. And our question here is, we really want to understand what is the tri-directional relationship among communication, machine learning, and control for this kind of system. So the challenges here are also big. So for example, this is a very complicated system, and to really make the entire system work, we have to have some learning-based approach because we don't know the full dynamic model of the entire system in general. And we have to deal with a lot of uncertainties here. So for example, autonomous vehicle, a lot of information comes from sensing part, comes from the computer vision part. We have to consider what if there's some wrong information or there's some error in our sensing, what will happen? And we want to make sure our decisions are safe and our decision-making framework work for this large-scale system in real time. So specifically, let's start from this kind of diagram. Say, okay, on streets, we have multiple vehicles and each vehicle has its own, like a LiDAR, a camera, and a GPS, this sort of sensor. And they can communicate with each other. Of course, we want to consider, say, communication protocol needs to be realistic. So for the computer vision part, they use their own capability to understand what is happening in the environment. And we will share mainly the 4 topics in the following slides. So the first part, we will talk about, okay, for the computer vision part, how we can understand our model uncertainty and quantify the uncertainty of deep learning-based computer vision results. And for the decision-making part, we will explain how we design safe and scalable multi-agent reinforcement learning-based methods for the autonomous vehicles to make their own distributed decision when they are running on streets. And we will quantify the benefit of these vehicle communicate and talk with each other through a reward relocation scheme to incentive them to do so. And finally, we will present our recent research results on robust MAR, even under state uncertainties. For example, if the vehicle's knowledge about the other vehicle's position or velocity has errors, what can they do? So feel free to ask your questions, just unmute yourself through the process of presentation. So the first part, let's see if we have communication capability, how we can help the computer vision part. So computer vision perception has really been a hot area, and people have designed a lot of different neural network structure to do, for example, object detection, object tracking, trajectory prediction, etc. However, a lot of efforts actually focus on improving the accuracy part, and there's not really much work on, okay, after we do some computer vision task based on deep learning model, can you please tell me, like, what is the model uncertainty here? So why we care about uncertainty? Thinking about the downstreaming tasks like task planning based on the object detection result. So if the deep learning model tells me, okay, the object detection is as this red box, but the ground truth is actually the green box. And we do path planning just according to this red box. What will happen? We can plan an unsafe path. So the issue here is we cannot just assume our computer vision model is 100% accurate. So the method we have been proposing here is, even we don't have an 100% accurate computer vision model for this object detection part, but if we use some ellipsoid, orange ellipsoid, to represent, for example, the covariance of our prediction on this location or position of each vertex, and then we can use a larger gray box to represent the position of this one object, then even our model is not 100% accurate, later in this path planning part, we can still guarantee safety. So in terms of that direction, basically our contribution is we define a method that we can quantify the uncertainty of object detection tasks. And we can calculate this uncertainty result in one inference. The result can be calculated in a really short time. And later we will show that through this method, we can actually both improve the accuracy of object detection and reduce the uncertainty. So what we do is just summarize in this one-page slide. So it includes both learning-based part and statistics-based part. So the learning-based part, we mentioned basically a lot of computer vision tasks is deep learning, deep neural network. And through the learning process, we add several additional output results. as a covariance matrix, represent like the positions of each vertex of the bounding box. And the loss function, we define it as some sort of a KL divergence loss with like reducing the volume of the uncertainty as one specific objective through the training process. And meanwhile, we also have a bootstrap-based calibration process that through the training process, we will partition the data set to training and validation data set that we will repeat the process of training and validation, also calculate the covariance of the prediction residuals. So with this kind of calibration, we actually have a better or more accurate estimation about our model uncertainty compared with only relying on learning-based method, because in the literature, researchers have shown that only learning-based uncertainty quantification can be over-optimistic. So with this method, what we can reach can be shown in this sort of video. So this video is showing in real time. So for example, in object detection tasks, usually people want to have 20 frames of object detection in 1 second. So with our method, we basically have this, you can see in this video, there is orange ellipsoid shown. So these are like the uncertainty quantification result we calculated together with this object detection result. So basically our method can be executed in inference stage very fast. And we show that our method can be used to quantify the uncertainty of different deep neural network structures of methods. So these are like a literature object detection methods designed by a computer vision research society. So our uncertainty quantification framework is pretty general, and we can compare on, for example, this is called the DiscoNet. This is a method that shares intermediate features for computer vision object detection tasks, and this upper bound shares like all the raw point cloud data to do the object detection. And here, the lower video, like the lower bound part basically does not share sensing environment. So it's every vehicle uses its own LiDAR point cloud data to do this object detection result. So basically, these are like a different deep neural network structures, and we can use our methods to quantify their object detection uncertainties. And here we also have tables to compare. The first table is about the accuracy evaluation with our method, and the second table is about uncertainty evaluation with our method. And here each column represents like one type of deep learning neural network structures to do this object detection task. And one row is some literature uncertainty quantification methods, and the last row basically shows our uncertainty quantification methods. So some interesting insights here is the first table actually shows by specifically considering reduced uncertainty as one objective through training, we can actually improve the accuracy of object detection result. That is good, means reducing uncertainty and improving accuracy. These two objectives, they don't contradict with each other. So before we really run the experiments, we worry about, okay, if we put uncertainty as some objective, what if it affects accuracy, right? But it turns out it won't. So it will actually help improve the accuracy in most deep neural network structures. So this is the one interesting insights. And another insight here shown on this second table is there are like a different uncertainty quantification methods in the literature, and we compare them with ours, and we can show that with our uncertainty quantification methods, we can have the best uncertainty reduction after doing this retrain and calibration process. So which means if we really think about uncertainty is some important factor we want to consider for the computer vision tasks. So indeed, we can have some method to improve that part of performance in terms of uncertainty. And meanwhile, we believe that in the future, uncertainty quantification can also be one important metric on evaluating models' performance when they decide, say, under specific scenarios, what kind of information vehicles should share with each other, right? So for example, if sharing that information helps reduce uncertainty, then basically the information has additional value, so we should consider to share, etc. So I think currently most evaluation metrics care about this accuracy part, but in the future, uncertainty can also provide an additional angle to evaluate what information we should share to really improve this computer vision task performance. So if you are interested in this paper, is already published, and also the data set and the source code, everything is online, so feel free to try. And recently, we also propagated this object detection uncertainty to the downstreaming tasks of object tracking. So originally, tracking can be a very difficult task if the detection part already has a large error. So it's even impossible for the existing algorithm to really like match, okay, this is the same identical object in frame 1, frame 2, and frame 3, etc. But when we propagate this uncertainty information, we can specifically show that, especially for objects with high occurrence, this uncertainty-aware object tracking method, the performance is much better compared with existing literature methods that did not really specifically take the uncertainty information at all. This method is also a recently published paper and source code available. So, yep. So these are our first section about the computer vision part, how we can do uncertainty quantification and also leverage the uncertainty information to improve computer vision accuracy and reduce the uncertainty. And now let's see on this autonomous vehicle decision-making part, what we can do. So for the decision-making, we consider a complicated scenario, say every individual vehicle at every time step with all this observation, like the computer vision part tells the autonomous vehicle, okay, the surrounding vehicle's positions, and with and the velocity estimations, with all this kind of observation information, each individual autonomous vehicle needs to decide at this moment, should I keep lane or changing lane, or should I keep lane in this current speed, or should I accelerate a little bit, but still within the same lane? And it also needs to decide, okay, if I want to keep lane, then what should be the detailed continuous control input, for example, steering angle, throttle, etc. So it's basically a hybrid decision space with both discrete actions to decide and continuous control input to decide. So it's different from the most existing literature method, like doing platooning. It's like, okay, all these vehicles exactly already know they want to do platoon, and then to decide acceleration or deceleration, staying within one lane. Or it's different from like a merging lane maneuvers. Say, okay, this vehicle exactly knows at this moment, I just want to merge into this lane, and how to decide this steering angle, accelerations, etc. So here, it's like every vehicle, it doesn't have this kind of high-level decisions yet. It needs to purely like decide by itself what to do at each moment. So we are basically designing like a fully autonomous solution for these multiple vehicles on streets. And another difficulty part or challenges we want to tackle here is from a single vehicle's perspective. It does not have the full knowledge of what the other vehicles will do exactly at the next moment, right? So every vehicle from a ego vehicle's perspective, the knowledge is through its own observation, or if communication is available through like shared information. But we don't know every vehicle has a full picture of what the other vehicles on streets will do exactly at each time step. So basically, this is a model-free setting from an ego vehicle's perspective. So basically, everyone here is doing distributed decision making instead of one centralized controller or one centralized decision maker is making these decisions for all these autonomous vehicles. From that perspective, we will design multi-agent reinforcement learning-based methods for our CVs. So I see some question here. Yeah, so there is one question about external factors causing error between autonomous vehicles, like those taken into, how will that taken into consideration in reinforcement learning? So maybe I will first introduce what we have been working on here, and then I can ask this question accordingly. First, some basic knowledge of multi-agent reinforcement learning. So the basic idea is consider we have some simulator, and then every agent in this simulator can have its own state and action space. And at every time step, it will randomly explore, okay, I will take some action AI at this moment. And then everybody has some action explored by itself, and then their joint action will go through this environment like the streets, and then they will get feedback about the specific reward they can get at this state by taking this specific action. The key difficult part compared with single agent RL is everyone's state and action reward at every moment. Everyone's reward at every moment is actually decided by the joint state and the joint action of all the other agents in the environment. So it self-selects action AI at a state SI, but actually the reward is related to the joint state and joint actions, means other agents do something that will actually also affect individual agents' reward. For a very special setting, for example, if all these agents decide to do coordinated behavior, then they can choose, for example, optimize the same reward function, optimize the same accumulated reward through the entire decision-making process. But still, they will need to learn their, for example, distributed policies instead of saying, okay, one centralized optimizer will decide the policy for all. And in the literature, some very popular framework to do this kind of policy learning can be centralized training, decentralized execution. Means through the training stage, we can train a very large-scale deep neural network to represent the critic or the Q function that basically learns the reward from now on. The agents can get by taking specific action, and then this large-scale Q function will be related to the joint state and action of all the agents. So actually, when the agents' number are quite large, then this training can take a very long time due to this curse of dimensionality issue. So that's really not scalable if we have a large number of agents. And to solve this kind of scalability issue, in our research, we try to design what we call a decentralized training and a decentralized execution method. So the basic idea here is instead of train a very large critic or Q deep network, we assume that every agent AI, it can communicate with this, for example, closest neighbors, like only the closest 3 to 5 agents through both the training and the policy execution stage. So then the Q function they will train is only related to these closest neighbors, or for example, it's related to these NK neighbors. And we can prove that this decentralized Q function, the approximation error compared with the centralized Q function is actually bounded. And from this perspective, then even the total number of agents can be 100, 200 or something. But actually, every ego vehicle, every agent I only focus on learning from its closest neighbors and then learn how to interact with these very close neighbors. And of course, here the result can be more general. So if we consider, say, the communication hub can be 2 hubs, 3 hubs, etc., and there will be in total like NK neighbors through these communication hubs, then this results generalized to like NK neighbors is communicating with agent I, and that's related to how this bond will change. So the first part is on the scalability. And there's another issue about safety. Say, if every agent only interact with the environment, or if there is only like a static obstacles, then it's easier to decide, okay, what path to take to basically just avoid that obstacle. But now we have autonomous vehicle is basically an dynamic environment, and there are a lot of other vehicles on streets, and there are also there can be human driving vehicles, other autonomous vehicles, or different types of obstacles, moving or static. So for the safety part, in the literature, there have been different methods like a theoretical guarantee and specific conditions, or how we can project unsafe action back to safe action space, etc. So specifically in this MARL setting, we need to consider every agent interacting with the environment, and agents, they are also interacting with each other. So for the safety part, we design a safe action mapping module that each agent I is responsible for its own safety checking. So the basic idea is we define some safety rules. For example, it can be based on the dynamic function of each individual vehicle. And every agent will check, say, this action explored by reinforcement learning. If it's unsafe, then this action will be filtered out. If it's a safe action, then it will be saved in the replay buffer to train the RL policy. So through this approach, so basically every agent is responsible for its own safety requirements, like no collision, and then the entire system can make sure, okay, there's no collision happening through this training and execution stage. And specifically, we can show some experiments we run in color simulator. So for example, here we compare our method with method no safe action mapping. So if there's no safe action mapping, then even during training stage, these cars continuously collide with each other. So the training is really hard to go on. And with our methods, then basically the training process can go smoothly, and these autonomous vehicles learn how to run like on this like different environment settings. Like we put different numbers of vehicles on like different maps, and we also put like a different number of autonomous vehicles and human driving vehicles. So human driving vehicles in the simulator is basically we don't control them, so just randomly spawn vehicles in this map. And we can see that after training by our methods, the autonomous vehicles can smoothly react to like a different number of human vehicles. If human vehicles do some lane changing, the autonomous vehicle will wait a little bit, etc. So basically, they can drive smoothly on streets. And we also want to show some specific scenarios like obstacle at the corner and how shared information like our velocities of each vehicle helps here. So without information sharing, this red autonomous vehicle can only see this obstacle after they already reached the corner and it's too late to change lane, so it forms a traffic jam. But if this red vehicles share their own speed, and then, for example, this following vehicle, it learns, okay, the leftmost lane average speed is turning very slow, and it decides to change to the middle lane even before it reaches the corner, because changing to the middle lane, it will have like a faster velocity. So basically, This shows with even like a very basic shared information like a speed of the autonomous vehicles, then it can be very helpful in scenarios like this obstacle at the corner. And we also have tables to compare our distributed decision-making method with the method, say, trained on like every autonomous vehicle has a full knowledge of the entire streets. So of course, that can be very slow because they need to have like a very large like a neural network function to take all this information. And we can see that actually our performance is pretty comparable with this kind of like a full knowledge scenario. And here, for example, the state information is set as a relatively low dimensional, like state information include position, velocity, acceleration, and also visual information here, basically object detection result. And the action here is also discrete action for the reinforcement learning part takes this learn keeping, learn changing, change left or change right. And we set up the reward function as every ego vehicle wants to optimize the same reward, say the average velocity on streets and also comfort. So comfort here is a penalty for like a very aggressive learn changing behavior. So we want to make sure there is no like a crazy driving behavior, like just always changing lane to get this high speed things. Specifically, like for the safety checking part here, we assume every ego vehicle has a bicycle model. And for doing lane keeping, the safety requirement is described as, say, maintain a safe distance. And specifically, we utilize the theory from control barrier functions to define, say, okay, by checking some specific quadratic programming function, quadratic programming problems. If this problem has a feasible solution, means at this moment keeping lane is doable. Similarly, for changing lane, we again define like a set of constraints that this this changing lane maneuver should satisfy. And if this quadratic programming problem has a feasible solution, means okay, at this moment changing lane is doable. And of course, for doing changing lane, we want to make sure there is a safe distance between vehicles on the current lane, and also there can be enough safe distance between vehicles on this target lane if this ego vehicle choose, for example, change left at this moment. So the constraints will be more complicated for changing lane maneuvers for sure. And then back to the question of how can RL take considerations of, for example, external factors. So I think external factors will affect both the efficiency in this system level and also safety on this individual vehicles level. So for example, for the efficiency part, we can go through, say, we might want to set up like a larger safety distance in bad weather. So then in general, like the traffic flow will be reduced in this sort of a scenario. And also, for example, in RL part, when there is like a different weather conditions, the information about maybe position, velocity, the error might be large. And actually later we will talk about like MARL under state uncertainties. So I think that can be a potential solution for these scenarios. And for safety part, for example, under good road condition or bad weather, the bicycle model actually will be different. So for example, if we know ego vehicles like a bicycle model in like a road or rainy, in snowy or rainy roads, then we can definitely use that part of model to check this safety requirements. I see there's also another question about congested network. The scenarios appeared more free flow, but what if the network was congested? Okay, so is a congested network, you mainly ask about the traffic flow part. Later we will also talk about like different scenarios. So I think we are solving kind of a different problem. So for example, if there is congested network, then basically average speed of vehicles on streets can be much lower. So basically, like the optimal speed every vehicle can reach might be slower than like in a free network flow. So, but still, as long as there is available solution. So, for example, when there's no space to really move on, then basically these vehicles will choose to stop. So, stop is also one action we can put in this RL decision making. Also, the vehicle choose to keep lane, but by this barrier function to keep safe distance, then they basically can decide like a very low speed of acceleration or even deceleration or like a throttle value. So basically, as long as there is available solution for these vehicles under like a congested scenario, so these RL frameworks that's still like applicable. Yeah, but indeed here we didn't specifically check this very congestion scenarios in the previous video. But actually, we do have some say. Oh, okay. So here we show the safety guarantee part. So the system always keep this safety distance. Then means okay. Well, we keep safety based on our action mapping module. And here we also want to show that maintaining safety is important to improve the efficiency. Like the black plot shows the baseline model, baseline MARL algorithm not having any safety module. So then it's hard for the algorithm to really like proceed the training process because there are so many collisions among these agents. So then the policy is really difficult to learn some like efficient policy to improve the speed of vehicles. And with our method, because we avoid those collisions, so the training can proceed. So these RL algorithm can gradually learn, okay, what can be a good policy, and then the total reward or the mean absolute reward is also improving through the training process. And we want to ask whether these RL algorithm can still have some good performance, even under very challenging scenarios. Like here in this traffic light, if some like a human driver or like some other like a bad autonomous vehicle is doing this very dangerous behavior, like running the red, violated the traffic rule, can these CVs really react to that? Also, in these scenarios, say someone suddenly parked on the highways, which another like very dangerous behavior, can these autonomous vehicles react to it? And these videos shows like existing baseline or literature methods. It's so hard for these autonomous vehicles to react to these like bad behaviors. And the question for us is, we assume these green vehicles, they can share their like basic information like their position, velocity, and their observed obstacles. So how can they utilize this kind of capability and coordinate with each other to make sure everybody keeps safe and no collisions and the traffic flow goes on smoothly? So the method we have designed here is first, we need a stronger safety shield to react to these abnormal behaviors. Basically, what we design is a more complicated second-order safety shield that can take this kind of acceleration, deceleration level of information for designing this constraints that the ego vehicle should satisfy. And then it can better react to suddenly deceleration, acceleration, or steering, this sort of behaviors. And another part of important design is the neural network structure. So actually, through the training process, the RL is learning under different scenarios how to react to the environment. So the representation of the dynamic environment will be very important for the RL. And here we design a GCN transformer neural network structure to represent the spatial temporal dynamics of the surrounding environment, like the other vehicles. For example, if some vehicles suddenly parked, so then it's like if you check its temporal sequence on this position and velocity, then this is some very different object compared with maybe other agents on the street. So this is something the RL algorithm should really pay attention to. So basically, we have a stronger and better spatial temporal representation for this dynamic environment and feed that part to the RL to let the algorithm understand what to react. And with these two parts, what we can achieve is shown in these videos. So we are comparing our methods with other methods that they do have the safe action checking module part, but just does not have the strong safety shield. So our method can improve both safety and efficiency of the traffic network significantly compared with the baseline use, just a very normal safety checking part. And we also compare our method on this, like a vehicle suddenly park on the highway scenario. Again, we can improve the safety rate and efficiency rate significantly. Here, safety, we mean no collision at all. So all these vehicles pass, no collision. That means safe. If any one autonomous vehicle has collision, no matter with this obstacle or with other agents, then that's not a safe scenario. And we also compare, say, this is more like a very like a congested network scenario. So there are like many running vehicles or agents on the streets, and we can see that it might not be enough space for the following vehicles to really react to this suddenly parked vehicle in this sort of scenario. So indeed, so for example, when we increase the congestion level of the streets, the safety rate can be affected compared with like a free network scenario. But again, our method has significant safety and efficiency improvement compared with baselines. And we also want to point out that the safety rate is affected significantly by like how challenging we set up the scenario. So for example, if we only put the vehicles in this kind of like a pretty sparse traffic network and not like very dangerous behaviors, human driving vehicles or environment vehicles, indeed, we can still have 100% safety guarantee. And here, for those testing scenarios, we are doing like a very edge case or very like difficult testing cases for these autonomous vehicles. Okay. And then the question is, in the previous slides, we already showed that if CVs, they do communicate and coordinate with each other, they can improve the safety rate, they can improve the efficiency. But we cannot just assume naturally they want to coordinate, right? So the vehicles might come from different manufacturing places, or say maybe passengers sit inside just don't want to share, don't want to communicate with the other vehicles on streets. Those are all possible. So sometimes for like coordinating with other vehicles to improve the entire system's efficiency, actually like a vehicle D, let vehicle C change lane to gain higher speed, and the entire traffic flow also has a higher speed, but vehicle D is actually yield and sacrificing its own benefit. So there might be like this kind of conflict of like individuals' objective with a system level objective, right? So then what can be an incentive design for really motivate these agents to coordinate with each other? And the methods we have designed here is called sharply value-based reward relocation scheme to like incentive or motivate the agents to coordinate to improve system levels efficiency. And the basic idea is like sharply value is a very classical concept in game theory. It's basically were first introduced in cooperative game in the static case, say how to quantify like the value of one player in the entire system. And recently in machine learning literature, it has been used to define like the value of specific feature or value of a specific data to improve the machine learning model's performance. And here we are first to define it in this MARL setting. Basically, one agent, if it contribute more to improve the entire system's efficiency, then through this training process, it will also get this additional reward through this reward relocation. Basically, we are not just assuming having the same reward for every agent they will coordinate. Instead, say if agent I is really contributing more compared with this like one collision including agent I or one collision not including agent I, then this will get the part of reward proportional to its contribution. And we can prove that this is an efficient reward relocation. The entire system reward is completely distributed to every agent for cooperative policy learning. And this is also a stable reward relocation if the game setting satisfies a convex game condition that all agents will choose to stay within the correlation, communicate with the others and the cooperative to optimize the system level objective. And we compare our method again, still in this CV environment, compared with, say, every agent just have the same identical reward function, compared with several like a baseline or several popular MAR algorithms in the literature. And we can show that with our method, we can improve the system level efficiency, like average velocity and average comfort in, like, for example, 10%. Is there an okay? Say, and now this is the last part of our recent work. Remember that we talk about the computer vision part can have error, and also the sensing knowledge can have error, right? So if our knowledge about the surrounding vehicle's position or velocity is wrong, then in this multi-agent setting, this will affect these agents' actions, right? So it might do wrong actions, and this can cause accident. So we show like a very naive simulation. Say here, basically we just manipulate or change the green vehicle's knowledge about the front vehicle's distance. Then it can do like a very wrong behavior and have a lot of collisions on streets. So then how we can solve this kind of issue? We first model this problem as a state adversarial Markov game. So we assume that the state information of agent I can be wrong, can be perturbed. We don't know how much it is perturbed, and we don't know its original correct state information at all. The only thing we know is we assume this perturbed state is still within the state space. So in the literature, theoretical machine learning people have studied robust MARL under, for example, transition function uncertainties or under reward uncertainties, etc., but does not really study the MARL under state uncertainties yet. So that's our like a sort of theoretical contribution to the research community. Say, if we define this problem as MARL with state uncertainties, then we first analyze under these scenarios, does the equilibrium still exist or not? So the equilibrium is defined in this Nash equilibrium flavor. Say, if only one agent changes policy or deviate from the equilibrium policy, then it won't get more benefit. So basically here, every vehicles or every system agent has wrong or perturbed state information, and we model the state perturbation as some adversarial agents deciding, okay, taking the correct state information, how to perturb the state information. And then basically this is the asymmetric information game. Adversarial agent has true state information, but the system agent only has perturbed state information. And we can show that under very specific scenarios, say when the state perturbation function is bijection function, then we can prove this robust equilibrium still exists. So however, in reality, it will be hard to say how is the state information perturbed, right? So we have no idea how wrong our knowledge about the other vehicle's position or velocity can be. So under those scenarios, it's hard to say we can find the equilibrium policy. Then the best we can do is to just maximize our worst case expected reward. So it's like, no, my state information can be wrong, but just want to make sure I'm still doing okay under the worst case wrong state information. And to solve that kind of problem, we propose algorithms. So it's basically putting adversary in the training process to perturb the state information. And we can show compared with several popular MAR algorithm in the literature, and our method indeed have the best performance in terms of mean episode reward, even under state perturbations. And recently we have also analyze how we can do this kind of algorithm in systems like CVs when they are also complicated dynamic process, because this wrong state information will affect both the efficiency of the entire system and also the safety of the system. And our method here basically includes several parts. So for this MARL part, we will have methods like how we can do this worst case Q network training to basically simulate the potential cases of wrong state information and consider that part of the effort through the MARL algorithm training to make sure that our trained algorithm is robust to state errors. And in the safety part, we also have what we call robust safety shield. Say we specifically consider, okay, for example, our knowledge about the other vehicle's position or velocity can be wrong, and how we do this safety shield checking to make sure under wrong state information, our behavior is not too bad, and the safety part is not violated badly. And basically, the testing results we can show is with our method, we can improve both the safety rate and efficiency significantly compared with other baselines. So the videos can be shown like this. So with our method, even we have a wrong position information about the surrounding environment of vehicles. So still, we can, for most cases, we can make sure no collisions. But with baseline methods, if we don't consider there can be wrong state information in the safety shield, then it can be, the safety rate can be reduced significantly. So we have a lot of different testing scenarios. For the time issue, we only show some here. And we do also have our paper already on archive. So if you are interested in, so please check. And in our lab, we have several F-intense vehicles. For individual vehicle, we check, for example, they can do this lane tracking, avoid obstacles, or they can do this changing lane maneuvers. And we also, we are still developing, see how these small vehicles communicate and coordinate with each other, and try to make sure, okay, they react well together on streets. And I think we can summary here this basically today we present our work on uncertainty quantification for collaborative perception when we have communication among vehicles, how we can reduce the uncertainty of the collaborative perception tasks such as object detection and object tracking. And we also want to emphasize that uncertainty can be one useful metric for autonomous vehicles to decide what information to share under different scenarios. And we show that with shared position velocity information among autonomous vehicles, they can improve both the safety and the efficiency through this learning and control process. And we show this improvement on safety and efficiency based on MARL algorithm work for both normal scenarios like a free network or challenging scenarios like people running the red or suddenly parked on the highway, etc. And we also show that considering state uncertainty for MARL is important because state error can come from a sensing part, come from a computer vision part, and indeed to maintain the safety and efficiency of the entire system, we want to have robust MAR method and state uncertainties. And uncertainty quantification on computer vision can really bridge the gap between the computer vision research society and reinforcement learning and control society to together make the autonomous vehicle, connected autonomous vehicles safer and more efficient in the future. And only one slide about what we have been working on for mobility on demand system. The question we consider is like Uber and Lyft. If we serve these mobility demand using autonomous electric vehicles, then we need to decide where to pick up passengers and where to charge, etc. And the main challenges we've been working on is the prediction about human mobility pattern and the prediction about available charging spot in the city that can be very inaccurate. And there will have a lot of uncertainties, and how we can take that part of demand and supply uncertainties in our decision-making framework. We have been working on both data-driven robust optimization and robust multi-agent reinforcement learning to make decisions under those supply and demand uncertainties. We have also been working on cyber physical system security, considering, for example, sensor environment can be attacked, and then how we can quickly detect these abnormal scenarios and also design a resilient scheme under these attacks. And here are my students, and also we have collaborators from different universities. And in the future, we will continue to work on MAR, specifically robust and safety MAR, and also uncertainty quantification. Hopefully, we can improve the safety, efficiency, and the resiliency of embodied AI in the future. And specifically, autonomous vehicle, connected autonomous vehicles will be one of our major challenge and motivation problems in the future. Yeah, so I think I can stop here and welcome for more questions.
All right, so thanks so much. I have one quick, hopefully easy one for you. What was that software, and I may have missed this, that was used to create those visualizations?
Yeah, so this is Color. So Color is open source, and I think all the researchers can use it.
Okay.
Yeah.
Yeah, it looked very cool. I want to go play around with that. And then I saw at the very end you were doing some, I guess, validation in the lab with like, little robot cars. Are you aware of any kind of larger scale validation tests?
Yes, for larger scale validation test, recently we just chat with Michigan's M-City. So they are doing this like multiple vehicle testing. They say plan to be start in October, and they would like to have our lab, our team as one collaborator on those kind of effort. So we already shared all these like results, these videos, the test cases we have been working on with them. Yeah.
Awesome. All right, so I'm not seeing any more questions in the Q&A. So I guess what brings us about to a 4. So I'll just reiterate, thank you for your great presentation, and thank you to our participants for taking an hour out of your day to come learn about this. And then, yeah, again, please check out our NEUT symposium. Professor Miao, I hope to see you there if you're able, if your schedule allows. But otherwise, we'll talk soon. So. All right.
Yeah, thank you. Thank you,
Yep.
everyone, for coming. Yeah.
Take care, everyone.